Alright guys, let's start. So yeah, go ahead and try to access those course videos and let me know if there are any issues. I'll try to resolve them. Okay, so let's get started and let's review what we've already talked about. So we've been talking about the whole point of statistics, and we were saying that there's some population that you want information about. Let's say you want to know for the whole country what percentage approved the president. So in that example, the whole country would be the population. Again, it doesn't have to always be the whole country. It's just whatever data set you're interested in. It could be just this classroom, it could be the world. It's just all the information you want to know about. So we said it was not feasible or not practical to collect data for the whole population. So instead, we're going to end up with some kind of sample, which is just a subset of that population. And then we said using that sample, we want to be able to infer a conclusion about the whole population. And that conclusion is done through statistics. So then we talked about after you make the conclusion. Last time we talked about communicating the results. And we talked about a couple important communication issues like correlation versus causation. Just because two things occur at the same time doesn't mean that one actually results in the other. And we talked about how you should pay attention to the source of the study when you're reading the study, because that could bias the actual results. So that's the big picture of how statistics fits in. So moving forward, we're going to spend a lot of time in this area, which is actually formulating the conclusion. But before we can actually get there, we have to spend time building up to that, building up the tools and the framework in order to get there. So today, we're going to focus on this part, which is we're going to assume that we have a good sample to begin with, and we talked about that last time. So a good sample involves what?
Randomly selected and large enough to represent the whole.
Okay, very good. So the sample needs to be random so that it's representative of the population. That's the best way to ensure that it's representative. And also it needs to be large enough to be accurate, but not too large so that it's not practical to collect. So the sample size is one issue, and the other needs to be random. Again, the randomness issue we've already talked about. Incompletion, we won't talk about it anymore. The sample size that's needed, we'll build up to it and talk about it later. So that's how you calculate the minimum sample size that you need for certain accuracy. So assuming that we have a good sample, we're going to collect some information. Let's say we're interested in what percentage of the population approves of the president. We're going to go around and ask people in our sample, do you approve of the president? So we're going to get a whole bunch of yes or no answers. And so from all those yes or no answers, we want to make sense of them. Or let's say we wanted to find what percentage, let's say we wanted to find the average IQ for the whole country. So in our good sample, we would go around and ask people in our sample, what's your IQ, or actually test their IQ for all people in that sample. And then we're going to get a whole bunch of numbers representing IQ scores, and then from those we want to make sense of those numbers. So the point in the class today is we have a sample with a whole bunch of data, yes or no, or numbers, and we want to make sense of those. So how do you think people go about making sense of data?
So you have to have a mean average, you have to have a high end and a low end.
Okay, good. So one way is we want to be able to summarize those numbers somehow. And one way to summarize it is to take all those numbers, crank it through a formula, like an average formula, and have it spit out a number that somehow represents something important about that data set. So this will be under summarizing data. And one way is through numbers like the mean, median. You might want to know what the total is. That could be a number. So later on, we'll talk about another number called standard deviation. That's also important. And the standard deviation is designed to summarize something important about the data set, which is called variation, which we'll talk about later. But the point is that all these numbers are coming from a formula, and these numbers summarize something important about the data set. Okay, and so besides summarizing data, we might also want to organize data. So how do you think people go about organizing a bunch of numbers?
Put them into a chart.
Yeah, good. So you use
Charts,
charts,
graphs,
graphs, good,
tables.
good. Charts, graphs, tables. Good. So in today's class, we're going to talk about organizing and summarizing data. So in particular, we'll start with the charts, graphs, and tables that we frequently use in class. So first concept we'll talk about is this idea of a distribution. So let's put it into context first, and then I'll define what it is. So let's say that you guys take an exam, and I collect all the test scores. And so let's say that these are the test scores. So let's say we have these six, let's say that there are only 6 students in the class. And so let's say we have these 6 test scores. So these are values of a certain variable, and that variable is grades. And so one way we might want to organize this data is we might want to list all possible values that this variable could take. Not just the values that we currently see in this data set, but all possible values. And then for each of those possible values, indicate how often they actually occur in the data set. So for grades, what are all the possible range for grades?
0 to 100.
Let's say 0 to 100. Okay. So we're going to indicate 0 through 100. And one way that you can do it is you could just list out 101 numbers from 0 through 100. But that's going to take up a lot of space. So what we're going to do is group the possible values. So let's say one natural way to group it is 0 through 10, and let's say 0 through 9. And then 10 through 19, and then 20 through 29, and so forth, all the way through 100. So you notice the way that we arbitrarily chose to group it is each group here, like the first one goes from 0 through 9, so there are 10 possible data points involved in that group. Then you go to the last one and it goes from 90 to 100, and there's 11 possible data points. And that's fine, we're just arbitrarily grouping them. So for each group, we then go through our data set and see how often each one occurs in the data set. So most of these groups will have a number of occurrence of 0. So the grade 0 through 9 occurs 0 times in the data set, and so forth. So what's the first group that has a non-zero entry?
79.
Yeah, good. So the seventies will have 2 occurrences. And then the eighties will have 1 occurrence. And then the nineties will have 3 occurrences. So this will be labeled as the first column will be the variable, in this case grades. And in general, we call this X your variable of interest. So in this case, it will be specifically grades. And then the second column will be how often that particular value occurs in the data set. So there are different ways we represent how often the value occurs in the data set. One way is just a raw count. We just count them up, and technically that's called a frequency. So just the number of occurrences in the data set is the frequency. So that's one way we could choose to represent how often the values occurs in the data set through a raw count or a frequency. How else do you think we could represent how often values occurs in the data set?
Use a histogram?
Yeah, so we're gonna build up to that. So essentially, you can ultimately convert these 2 columns into a histogram. But before that, what's an alternative column that you could use besides the second column that represents how often the values occurs in the data set? So instead of a raw count, an absolute count, maybe you could do a relative count in the form of a percentage. So how would you convert each of these into percentages of occurrences? So the zeros will end up just being 0, but instead of saying that the 70s occurs twice, how would you express that as a percentage of occurrence?
The number of occurrences of that data point divided by the total amount of data points and then divide by 100?
Times 100%.
Times 100%.
Right, okay, great. So instead of just saying that the 70s occurs twice, we can say that the 70 occurs a certain percentage of the time represented by 2 divided by the total number, which is 6. So it occurs 2/6 of the time, which as a percentage would be 2 divided by 6 times 100%. So this would be 33 1/3%. So then how would you express the percentage for the ones?
1 divided by 6 times 100%?
Yep, 1 divided by 6 times 100%, that ends up being 16.6 repeating percent. And the last one, the 3 occurs 3 out of 6 of the time. Yeah, that ends up being 50%. 1/2 of 100%. Okay, so already we see that there are different ways to represent the same information, which is how often these particular values occurs in the data set. One is just a raw count or a frequency, and the other alternative, the third column, is representing how often the values occurs as a percentage of occurrence. So collectively, if you only look at the first and the second column, the values as well as the frequencies, then that's called a frequency distribution. So the first 2 columns is a frequency distribution. And then if you choose to represent how often the values occurs with a percentage, then you would be looking at the first and the third columns, in which case that distribution would be called a relative distribution. So the first and the third columns would be a relative So the point is that in a distribution, you're looking at a certain variable. In this case, the variable is grades. And then for that variable, we're looking at the relationship between all possible values of that variable in our data set, as well as how often each value occurs in the data set. So already you see these two different ways that we could choose to represent how often the values occurs. But later on, you'll see yet another way, which is a probability, and we'll talk about that when we introduce probability. Okay, so this is one way that we could choose to represent a distribution, which is a table of two columns, either the first two columns or the first and the third column. How else do you think we could choose to represent a distribution? So instead of a table of two columns, you could convert the columns to a graph with two axes, and each column is represented by an axis. And so let's look at that. Okay, so we have these two axes. And let's say that the x-axis is our independent variable, which we'll call our variable of interest, grades in this case. And the y-axis will be how often each one occurs, and then we could use either the frequency or the percentage. So let's say we choose to represent it using the frequency. So then basically we're just moving the values in each column over to the graph. So for the grade variables, we're going to go 0 through 9. Okay, so there's several ways we could do this. So one way that we could do it is for each, we could label the basically the middle of the group. So this group we can say represents the 0 through 9s. This group we can say represents the 10 through 19s. And then the 20 through 29s and so forth. So basically we're just labeling what each group represents. We're labeling the middle of the group. And then for each group, we just look at how often they occur, and we're going to have a bar with a certain height that represents that entry. And then so when we encounter the 70s ultimately, so let's say the 70s are here, then that would have a frequency of 2. So the height of this bar would go to 2. And the same thing with the 80s. Yep, 80s is 1. And the 90s is going to be 3. So this is one way that we could represent that distribution, and basically it's just a distribution that is represented by this bar graph, and we call that a histogram. So a histogram is a distribution that is represented using a bar graph. Okay, so here we chose to label the x-axis here with basically describing the name of each of these groups. So this group is 0 through 9 and so forth. But let's say that we chose to label these values at the boundaries, at these endpoints, rather than in the middle. So if we chose to do that, if we chose to label just the endpoints, it would start looking like this. And then you'd end up getting a lot of clutter. Because you have 0 through 9, and then you have 10 through 19 for the next class, next group, and then 20 through 29 for the next one. And so you start getting a lot of clutter for those labels. So how do you think you could resolve that?
Just do it in sets of 10.
Yeah, so let's try that. So if we did 0 through 10 and then 10 through 20. So the issue with that is because we're labeling the boundaries and not the actual groups. The issue with that is, let's say we have a data point in our data that's exactly 10. Well, if we're looking at the table form, then it's obvious which group 10 should go into. It should go in the second group because the second group involves only entries from 10 through 19. But if we look at the way we labeled our table, 10 is right on the boundary, so it's not clear whether a data point of 10 should go to the left or right of that boundary. So how do you think we can resolve that? Versus before, if we had labeled 9 and 10, then it's clear that the 10 goes to this group on the right. But how do you think you can resolve that to both make it clear and also resolve the clutter?
A note on the side saying this is representative of what?
Right, like a legend, okay, that works. What else? So legend is good, but it's like one step more to kind of, the reader would have to go through, and you want this to be as clear as possible immediately looking at it. Yeah.
Use half values like 0.5.
Okay, so what would this be here? So for this label, what would you label this?
9.5.
Okay, good. So 9.5, and the reason for that is we don't anticipate an actual data point that is right on the boundary of 9.5. So that's coming from the average of the last value in one group versus the first value in the second group. Just take the average, and you're gonna get 9.5. So that's a value that's supposed to be a boundary value, and you don't expect any data point to actually have that boundary value. So any data point can be safely on one side or the other. So that's what we'll do. If we choose to label the boundaries, then we're gonna take the average of the limits of each of the subsequent groups. So this one will be 19.5, this will be 29.5, and so on. So let's see. Okay, so this is just an example of a histogram, and again, a histogram is just a distribution that's represented using a bar graph. Okay, so in your book, in chapter 2, you'll also see a lot of other graphs being mentioned, and I just want to let you know now that all those graphs, you don't need to memorize them as just being lists of different graphs. Basically, all those graphs are just types of histograms. So they're really just different flavors, varieties of histograms. So let's talk about that. So this will be classified under types of histograms. So the first type of histogram is a dot plot. So I accidentally erased my data set. What are the 6 points?
72, 76, 82, 91, 95, and 97.
Okay, thank you. Okay, so rather than represent this distribution using this histogram, another way that we could represent the distribution is through a dot plot. So a dot plot is basically, instead of a bar with the appropriate height for each group, we're gonna have the appropriate number of dots for each group. So for the 70s here, instead of a bar with height 2, we're gonna have 2 dots stacked on top of each other. Instead of a bar with height 1 for the 80s, we're gonna have 1 dot. And a bar of height 3 will have 3 dots. So that's all a dot plot is. So it's a histogram. Instead of a bar, it'll be vertical dots. So this seems like a trivial difference. So what do you think an advantage might be over this dot plot versus the original histogram? Or disadvantage?
The bigger the sample, the harder it is to actually read.
Okay, so it might be a disadvantage and that it might be hard to read if you have a large number of dots, large number of data points.
Current area, and the good part about it is if it's small enough that it's legible, it's very easy to see where everything falls at.
Okay, and vice versa, if it's a smallish data set, then it'll be easier to read.
With the dots, you can like clearly see how many values are there. But with
Okay.
like a bar graph, if there's a lot of values, the values at the very far right are gonna be hard to like read all the way to the left and figure out what they are.
Okay, very good. So if there's a smallish number of data points, then it'll be easier to count or at least estimate the number of dots versus to have to align your eye to the axis to see the actual value. Okay, good. Any other comments?
It'd be easy to tell like which way it's skewed, like the shape of the data.
Okay, that's possible. So would it be easier or harder to see the shape of the data if it was in the form of a histogram with bars?
I think it'd also be simple to tell.
Okay, so it might be easier to see the general shape. Okay, good. And then what about in terms of constructing the graph? That you guys mentioned in terms of reading or interpreting the graph, but what about if you had to actually make the graph? Which one would be easier?
Also completely variable about the size. So if it was small, it would be very easy to make. If it was large, it would be hard to make that accurately.
Okay. So let's talk about some of you guys are going into computer science. So there's a thing in computer science called computational complexity, where you basically analyze how hard or how long it would take to run. So imagine if you had to construct the original histogram. And so if you had this data set and you wanted to draw this histogram from scratch, meaning you wanted to go through and draw what the heights of all these bars should be. So then let's say you start at the 0 through 9, and you want to know how high this bar should be, and it should be a height of 0. But you don't know that until you go through your data set. So then you go through your data set, and you have to count how many 0 through 9s there are. And so just for this group, you have to go through your entire data set once. And then for the second group, you have to go through your data set again once, all the data points. And then for all these classes, you have to go through your data set exactly once to know how high the bar for that class should be. So basically, you have to go through your entire data set how many times? Yeah, so the number of classes that you end up having, the number of groups you end up having. So that's for a histogram, you have to go through your whole data set, the number of groups that you have, in this case 10 times. But let's say that you have a dot plot. How many times would you have to go through your data set to construct the entire dot plot?
Just one.
6 times.
Yeah, why is that?
6 times?
Yeah, 6 times, which is only once in your data set. So you only have to go through your data set once,
I got you, yeah.
right?
Yeah.
So why do you only have to go through your data set once?
As you're reading it, you're marking it.
Yeah, as you go through each point in your data set, you just put in a dot in the appropriate position. So you only have to go through your entire data set just once in order to have all 6 dots. And in contrast, for the histogram, you have to go through your entire data set 10 times, as opposed to just once. And so you might be thinking, well, that's great if I'm doing this by hand, but who does anything by hand anymore? We have computers. So it turns out that even with a computer, if you have a very large data set, like 1 million data points, billion data points, then this difference is noticeable. Even behind a computer, you can actually tell the difference in the computer crunching this out. So a dot plot will take faster to construct than a histogram. Any questions? Okay, so that's a dot plot. Let's talk about the next variation, which is a stem and leaf plot. So in a stem and leaf plot, the first thing is, instead of labeling the boundaries, you label the actual group itself. So for here, the boundaries are 69.5 to 79.5, so we can call that the 70s, let's say. But instead of just calling it the 70s, we're going to label just the most significant digit. So the most significant digit of the 70s is 7. So of the 80s, it'll be 8. Of the 90s, it'll be 9. And then what we'll do is, instead of an appropriate number of dots, we'll indicate the least significant digit along with that group. So for the 72s, we'll put a 2 there to indicate that least significant digit of 2. And then there's going to be a 6 on top of that where the 70s are. And then for the 80s, we'll have an 82, so we'll indicate it with this 2. And then we have these 3 90s, 91, 95, 97. So what numbers go there? 157. So 157. So this is all the stem and leaf plot is. So instead of a dot plot with the correct number of dots, you have the correct least significant digit in that group. So what do you think the advantage of a stem and leaf plot is?
For small numbers, very easy to put down, correlate, and make a result.
Yeah, so you can easily see the actual values in your data set.
How would you label it if you had more than 172 or any?
Okay, so good question. So what if you had duplicates, like duplicate 72s? So that adds to the advantage of a stem and leaf plot because you can just stack the 2s up. So then just by looking at it, you see how many duplicate values you have.
6.
Thanks. Okay, so this is stem and leaf plot, and in this case, so first of all, this seems like it has a cumbersome name. Why do you think it's called a stem and leaf plot?
The stem is the bottom, and all the leaves are what you're stacking up coming off that line, or branch or limb, however you want to relate it.
Yeah, so it's there's an analogy to plant biology, right? So the stem is the most significant part of the plant, and as it branches out, it becomes less significant. You see the leaves of the plant. So again, the most significant part is the stem, or the x-axis in this case, and then the leaves are these individual members the less significant digits. So here we chose to represent the stem with the x-axis, but you could very well choose to represent it as the y-axis, so basically rotate this thing 90 degrees, and so this y-axis will be the stem, and then the leaves will come horizontally out. Any questions? Okay, so the next variation of histograms that we talked about. Yeah, so a better way to say this, instead of types of histograms, is variations of histograms. And so the next variation of a histogram has a very complicated sounding name, a frequency polygon. But it's very simple. All it is you look at your original histogram, and then for each group here, there's a bar of a certain height. We're going to label the midpoint of each of the bars. And then we'll just connect all the dots with line segments. And so this resulting line graph, only the blue part, is a frequency polygon. So the frequency polygon is only the blue part, the blue line graph. So what do you think might be an advantage of a frequency polygon over the original histogram?
Lots of ways to plot and overlap that.
Oh, is it? That's a waste to plot.
Plot and overlap that, so you just put that on a different, you could compare that data to another graph of a similar nature very easily just by overlaying it.
Yeah, excellent. So basically, if you had different distributions that you wanted to compare, like for example, let's say these were grade distributions, and you want to compare the grade distributions in different classes of students, then you could just put the three line graphs all on top of each other, and it'll be easier for you to compare the trends or the overall graph for the different graphs. Versus if you had the original histogram, it's much harder to compare them by stacking them on top of each other. You just have bars everywhere.
Or dots, or numbers.
Or dots from those, exactly. But again, this line graph allows you to compare different distributions easier by stacking them on top of each other. Or putting them on the same graph. Just as a visual example of that. Let's say that these are the grades of the 6 students in this particular class, and let's say you had another class with another number of students, and you want to compare their grades. You might see a line graph that looks like this. And so maybe these represent two different distributions of two different classes, and so you would want to be able to quickly compare how the students would do. Okay, any questions? All right, so let's talk about the next variation of histogram. And this will be called a Pareto chart. So, let's put this in the context of an example first. So let's say that you had this pie chart. And let's say that you go out and you ask people what they think contributes the most to happiness. And let's say then you plot the results using this pie chart. And let's say that there's a certain percentage that say that family contributes the most to happiness. And then there's a certain number that says friends. And then a certain numbers say maybe TV, and then another number maybe say video games. And then a certain number say pets. And then music. And then sports. And then something else,
Money.
oh, sure. And then maybe, what is it?
Health.
Health, good. So let's say that you plot the results on this pie chart. Do you think this is a good way to visualize that data?
No.
No. Besides that I drew it badly.
I'm not going for, visual arts over here, but there's too many ways to, tie all those together. Where too many things are overlapping, too many things can distract from one or the other, so I don't think you're gonna get a very unbiased answer on there to give you that data. Because it may not be your health that's making you upset. Friends may have gone off and then come back and things have changed. There's too many ways that information gets skewed that way.
Okay, so the first comment is you probably maybe after you get all this data, maybe filter it somehow, or maybe you could clean up the categories a little bit. But apart from that, let's say you wanted to depict just the raw information for now. Just looking at it, is it easy to tell the relative difference between the groups? For example, is it easy to tell the difference between TV and video games, how big of a difference that is? No, not really. They look really close together, right? And so one thing you might want to do is at least label it with some actual numbers. But for now, we're just talking about the visual aspect of it. Is it easier to just look at it visually and tell the relative differences, despite not having the numbers there? So no, it's not easy to tell the relative differences just by looking at this. So to correct for this, one thing that we can do instead is this thing called the Pareto chart, which is we actually construct a bar graph, but in descending order of the value. So here the family is the most, so we're gonna have a certain bar graph that corresponds with family. And then the next one will be friends, so maybe friends will be here. And then next one might be, looks like money. And then, well, health looks like, yeah, health, let's say health. and then so on. And then basically, you just sort them in order of decreasing order of height. So just by looking at it, you can tell the relative differences really easily. So all this is a bar graph, but in descending order of height. So same thing here. If you wanted to construct a Pareto plot for this histogram, you would basically just reorder these bars with descending order of height. So the 90s would go first, and then the 70s, and then the 80s, and then everything else goes after, and it doesn't matter the orders of the other ones. Okay, so in this case, if you wanted a Pareto chart, you'd have these bars in descending height. And then this would be the 90s, the 70s, 70s, 80s things.
In the 80s.
80s things. And then it doesn't matter the order of the ones that all have 0 heights that follow it. Any arbitrary order is fine. So you can do 10s, 20s, 30s, and so on. Okay, so this would be a resulting Pareto chart. So Pareto was just a mathematician who came up with this idea. It's a very simple idea, but he still has his name eternalized for it. Hopefully you guys will be the first ones to come up with a simple idea so that you can name yourselves after it. Any questions, comments? Okay, so these are the types of histograms that we talked about, and again, the point is that there's nothing special about these types of graphs. All they are variations on histograms. They communicate the same kinds of information that a histogram would, which are the relationship between all possible values of a variable, as well as how often they occur in a data set. Okay. So let's say that we had the original histogram up. Let's say I choose to label the actual groups. So 70s occurs 2 times. So by looking at this original histogram, you can tell the relative shape of it with the heights of these bars. And remember we said that a histogram was all values of a variable along with how often each one occurs in your data set. Here we chose to represent how often the values occurs as a frequency. But let's say we had chosen to represent how often the values occurs as a percentage or a relative distribution. Then would the relative shape of the graph be the same? So by relative shape, we mean we have all these 0 heights, and then suddenly we have these 3 shapes where the first one is twice as high as the second one, and the second one is 3 times lower than the third one. So would the relative shape of the graph be the same if we chose to represent how often the values occurs using percentages versus the original absolute counts or frequencies?
No?
So you're saying the relative shape doesn't change, or the relative shape is the same?
The relative shape doesn't change.
Okay, why doesn't it change?
Because even if you express it as a percentage or as the number of occurrences, they're all still compared to each other, like they're still the same size compared to each other.
Okay,
Makes
good.
sense.
Good. So the relative shape should not be different, and the reason for that is if you went to construct, both distributions, and compared the relative shapes, they would be the same. And so if we're to, really the only difference is for the height of each bar, for the 70s, instead of being a height of 2, now you convert this to a percentage. And how did we convert each of these numbers to percentages?
Dividing the sample by 6.
Dividing by 6 and then multiplying by 100%. So basically, all we're doing is changing the value of these labels, and besides that, the actual picture of the shape stays the same. Okay, so the point is that no matter how you choose to represent how often the values occurs, relative, whether it's a frequency or a percentage or later a probability, the relative shape of the distribution is exactly the same. And that's important because later on in the semester, I might just slap on a distribution and draw the shape of the distribution and not bother to label this y-axis, which is how often the values occurs. But the reason for that is it doesn't matter, the relative shape will be the same. Okay.
I'll solve for y.
So let's talk about the next idea. Is, let's say we look at a particular variable like IQ scores. And let's say we're interested in looking at the distribution of IQ scores, which are, again, on the x-axis, we look at all possible values of IQ scores, along with how often they occur. And let's say that our data set is the population. Let's say it's the whole country. So we want to know in the whole country, what is the distribution of IQ scores? So it turns out that around 100, there's going to be a lot of people who have that particular IQ score. And then as you move away from 100 in either direction, and you plot the frequencies, it'll look something like this. So this is the original histogram that you constructed from your data representing IQ scores in the whole country. So around an IQ score of 100, there's going to be the most people in the country who have that IQ score, and as you move away from 100 in either direction, there's going to be less and less representation of that particular IQ score. And if you look at the general shape of this, it's what we call bell-shaped. So this is a bell-shaped distribution. We also call this a bell curve. So in a bell curve, you have some value that occurs the most often in the population, and as you move away from that value, it tapers off in both directions. But not only that, but you notice that this bell-shaped curve is symmetric. So you can imagine a mirror where that value that occurs most often is, and both sides are roughly mirror images around that mirror. So IQ scores are one example of a variable that is distributed as a bell curve in real life. What do you think might be examples of other variables that are distributed as bell curves?
Class grade averages.
Okay, so the suggestion was class grade averages. So the short answer to that is maybe, maybe not. So it depends on the difficulty of the test. Let's say that you were taking a test that ended up being really easy. So the test is really easy, and you're gonna get a lot of grades that are really high. And then you're gonna get virtually no grades that are low. And this might be what a distribution looks like for a test that's really easy. Like a lot of people score virtual hundreds.
So not symmetrical.
Exactly, so this would not be a bell curve. But if you had a standardized test, like the SAT, FCAT, and so forth, all these other standardized tests you take throughout your lives, then standardized tests are designed so that they end up having bell curve distributions. So, so an example of a variable that is distributed as a bell curve would be a standardized test. Any other examples? So Q-scores is one, standardized test scores.
Just to be grumpy, you want to see gas prices right now, but still, I don't know if it's gonna go back down, but I hope it does.
Yeah, it's possible, and that's a good example. The example was gas prices. And to really know for sure, you'd have to look at the data set and then plot the histogram. And if it has that shape, then yeah, it's a bell curve.
So instead of saying gas prices, where you have more historical data on that to look at it, you'd say like stock investments, looking at the history on back.
Yeah, possibly. So for a certain stock, for example, maybe if you look at historical data on that one particular stock, it might look like a bell curve. So let me throw out an example. What about income distribution in the US? Do you think that's distributed as a bell curve?
No.
Okay, so first of all, in order to know for sure, we would need to have all the data in front of us and draw the histogram. But even so, we could just do it based on our collective experience. So in order to get a good feel for whether a variable is distributed as a bell curve or not, you could ask yourself, from our collective experience, what do you think the average income in the US might be?
50,000 a year?
So let's say 50,000. So at 50, if it were a bell curve, then the peak would be at 50. But also, if it were a bell curve, as you move the same direction, if you move the same amount on each direction, the height of that bell curve should be the same. It should be roughly symmetric on both sides. So let's move the same in either direction, and let's move 40,000 so that we get 90,000 on the right and 10,000 on the left. Do you think the same number of people in the US make 10,000 versus 90,000? Again, we would need the data to know for sure, but just from our experience, likely not. So the number of people who make 10,000 is probably a lot more than the number of people who make 90,000. And because that lack of symmetry, this would not be a bell curve. Any questions? Any other examples you can think of that might be distributed as bell curves?
Like if all of the class had to drop down and do push-ups, like, most of us would be able to do a certain amount, and then there'd be a few outliers on each side.
Okay. That sounds like a great experiment.
That's the only thing I could think of.
Okay, good. So that could be the number of push-ups that we can do, and so we would build a histogram of, for each number of push-ups, how many people were able to do that. Okay, good. Any other examples you can think of?
Would weight percentile be something?
Okay, very good. So it turns out that weight is definitely distributed as a bell curve. So if you plotted the different weights and then plotted how often each group of weights was represented in the population, then it would definitely end up being a bell curve. So also it turns out the height distribution is also a bell curve. So these are just examples for now, so that we get a good intuitive idea of what it means to be a bell curve. Later on in the semester, we're gonna talk about bell curves in excruciating detail, but that's something to look forward to later.
This is gonna sound like semantics, but I wanna ask anyway, so it's like bell curve being symmetrical on both sides, is it precisely symmetrical?
Okay, so good
Or
question.
Is there a variable in there that says, yes, it has that kind of shape, but it's not perfectly symmetrical?
Yeah, good question. So it turns out that mathematically, a bell curve is perfectly symmetrical, but practically speaking, if a variable is distributed as a bell curve, then the more data points you sample, the closer that distribution will end up approaching the mathematical true symmetry of the bell curve. So, for example, we know that weight is distributed as a bell curve, but if you only sample, for example, 100 people, then you're not going to get a perfect bell curve. You're going to get rough symmetry on both sides. But if you end up sample a number of people that approaches infinity, like 1,000,000 people, then you're going to end up getting something that's almost exactly symmetrical. Okay. Any other questions? Okay, so we've talked about organizing data through distributions and these different types of graphs that represent distributions. So now what we'll do is we'll talk about how to summarize data. So we talked about organizing data, we'll talk about summarizing data now. So summarizing data means that we have a whole bunch of numbers and we want to be able to condense all those numbers into a single number that describes something important about the data set. So the first important thing that we want to describe on the data set is we want to describe the center. So the center is the most typical value. So, for example, if I gave you guys a test and looked at all your grades, then how would I describe or report to you what the most typical value in the class is, most typical grade? If there were 20 students and had 20 different grades, how would I report, okay, the most typical grade in this class was so-and-so.
The average or the mean?
Okay, good. So one way that people describe the center is through the average or the mean. So the average and the mean. So these are exactly the same meaning, average and mean. So how would you go about calculating the average or the mean?
The total divided by the number of samples.
Yeah, very good. So you just add up all the numbers in your data set, and then divide by the number of numbers. So this will just be the total divided by, I'll just say the total value, divided by the number of numbers. So remember, even on the first day of class, we made a big stink out of the distinction between a population and a sample. So anytime we talk about any type of measurement in this class, we'll also make that distinction between a population measurement and a sample measurement. So for this mean, we'll make this distinction between a population mean and a sample mean. So all this distinction is if your group of numbers happens to represent a population and you find the mean of that group of numbers that represents the population, then that mean will be a population mean. If the group of numbers that you're looking at represents not all the numbers you're interested in, but only a subset of the numbers, then that would be a sample of numbers you're looking at. And if you take the average of that sample, then the average would be a sample mean. So it just depends on, so the type of mean that you're dealing with depends on the type of numbers that you found the mean for, whether it represented a population or a sample. Okay, so the first thing is, there's a difference in notation between the two. So in this class, I don't expect you to memorize formulas. On tests, you'll actually be able to use formula sheets. But the formula sheets will list the formulas with specific variables that notate what these concepts are. So the population mean, for example, is given by this symbol. This is a Greek letter mu. Looks like a fancy M or a fancy U, depending on how you look at it. And then the sample mean is given by this symbol, lowercase x with a bar over it, for x bar. And so for either case, you're just adding up all the numbers in that group and dividing by the number of numbers. So in math, when you're adding things, that's given by this notation. This is Greek letter sigma, capital sigma, which denotes adding everything to the right of the sigma. So for the case of a population, if you want to add up all the numbers in the population, we say to add up all the x's. So each x, each capital X represents each data point in that population that you're adding. And then after you've added up all the numbers in the population, you want to divide by all the numbers in the population. And the number of numbers in the population is given by capital N. So this is the symbol for the population mean, as well as how you calculate the population mean. Just add up all the numbers in the population, divide by all the number of numbers in the population. Okay, any questions? All right, so same thing for the sample mean. The sample mean is abbreviated as the symbol x bar. And to calculate it, you add up all the numbers in the sample. So add up all the lowercase x's, which is each data point in the sample, and divide by the number of numbers in the sample, so divide by lowercase n. Okay, so the first thing is, you should also be comfortable calculating these means on your calculator. So if you have your calculator, you can take it out. But basically, if you have a certain data set, for example, some grades.
You have 72, 76, 82, 91, 95, and 97.
Okay, thanks. So let's say you had that original data set of 6 numbers we put up before, and let's say that this represents a population. You're told that this represents a population, all the numbers that you care about, and you wanted to find a population mean. So either you could just add up all those numbers and divide by 6, or your calculator also has a statistical mode where you can just enter these 6 numbers in and just punch mean, or punch the button that calculates the mean, and after punching in just these 6 numbers and nothing else, it will give you the actual mean by adding up the 6 numbers and dividing by 6. So every calculator is a little bit different. After class, I can show you for your specific calculator if you want. Otherwise, you can Google the specific model of your calculator to see what the keystrokes are. But either way, if you want, you can see me after class, and I'll go over your specific calculator. Okay, so, that's the mean. Let's say that we had a data set that looked like this. So let's say this is our data set, it's just given as a list of numbers, and asks you to find the mean of this data set. So all you would do is just add up the numbers and divide by the number of numbers. But let's say that this data was presented in a different way, but it's the same data, just presented differently. And let's say that we list only the unique numbers. So what are all the unique numbers?
4, 5, and 6.
Yeah, 4, 5, 6. And then for each unique numbers, we indicate how often each one occurs.
1, 3, 4.
Yeah, so the 4 would occur once, the 5 would occur 3 times, and the 6 occurs 4 times. And so the first column here is values of a particular variable that we call x, and the second column is how often each one occurs, or frequency. So we've actually seen this before. This is a frequency distribution. So this same data is being represented as a frequency distribution. So if you're asked to find the mean of this frequency distribution, basically you're finding the average value of x, but taking into account how often each of the variables actually occurs. So if you're trying to find the average value of this frequency distribution, why wouldn't you just want to add up the 4, 5, and 6 divided by 3?
Because you missed how many times they occur.
Yeah, because you're not taking into account that these numbers are being weighted differently. The 4 is only occurring once versus the 6 is occurring 4 times as much. So to find the average value of this frequency distribution, it would be the same average value as if you were to add all the numbers that appeared in this list. So given this frequency distribution, to find the mean of the frequency distribution, imagine just listing out each value that number of times and finding the average number in that list. But another way to do it is, you know that the 4 should be added up once, so that's 4 times 1. And then the 5 needs to be added up 3 times, so that's 5 times 3. And then the 6 needs to be added up 4 times, so that's 6 times 4. And then we're going to divide by the total number of occurrences, which is indicated by which column? Or,
That frequency column.
yeah, so you add up all the numbers in the second column, the frequency column. So this would be the mean of the frequency distribution, assuming this is population mean. So all we do is add up the products of all the rows and then divide by the sum of the second column. So that's for the specific example. What if we had to come up with a formula for this in general variables, general terms? So let's say I gave you a table of 2 columns, where one column is x, and one column is the frequency, or f. How would you come up with a formula, the same formula that basically allows you to calculate that mean that we calculated before? But now, instead of these specific numbers, we work with variables. So basically, you can think of it as each value in the first column are the x's, so this would be x1, x2, x3. And each value in the second column would be the f's, so this would be f1, f2, f3. So in this calculation for these specific numbers, we're just adding up the 4 times the 1, which is x1 times f1. And then we're adding that with the 5 times 3, which is just x2 times f2. And then we're adding up the 6 times the 4, which is just x3 times f3. So what's a compact way of saying x1 times f1 plus x2 times f2 times x3 times f3? Compact way of saying that is to sum up all the x times f's. And then, instead of adding up the s, or f1 plus f2 plus f3, what's a compact way of saying that?
That would be the capital N.
Well, capital N is the number of data points, but here you're actually adding up all the frequencies to represent the number of data points, but in order to calculate capital N, that would just be the sum of all the f's. So instead of saying f1 plus f2 plus f3, we say just add all the f's. So this is the formula that you'll see to find the mean of a frequency distribution. And this is also called a weighted mean. Because you can think of the two columns as having values for x, and the second column as having the weights associated for each value of x. So this frequency can also be called a weight, because each value is weighted with a certain value, with a certain number. So to find the weighted mean, or the mean of a frequency distribution, it's simply this formula, and this formula really is nothing more than add everything up and divide by the number of numbers. Okay, any questions? All right, let's do an example. So let's say that you were taking a certain number of courses this semester, and you're taking one course that, well, let's say each course has a certain number of credits, and then for each course, there's a grade that you get at the end. So let's say that you take a particular course that happens to have 5 credits. And because the class is worth so much, let's say you study a lot for it, and you get an A. But let's say there's another class that's not worth very much, like 1. Maybe there's like a bowling class offered. And let's say that because it's not worth very much, let's say that you kind of put it off and you end up getting an F in it. So let's say there's another class that's 3 credits, and you end up getting a C. So the question is, at the end of the semester, what should your average grade point be? What should your grade point average be at the end of the semester? So the first thing is, let's convert each of these letter grades into numerical grades. So an A is conventionally worth how many points?
4.
Yeah, 4. If you have a 4.0, you have all A's. And an F is 0, and then a C is 2. So the question is, can you find your average grade by adding these 3 up and dividing by 3? So if you did that, you'd get 6 divided by 3, which is 2. So should your average grade at the end of the semester be 2.0?
No.
Yeah, no way.
Because the classes you got in the A is weighted more.
Okay, very good. So this A that you got is in a 5-credit class, which is weighted, should be weighted 5 times more than this F that you got in the 1-credit class. So only if all these, grade values were weighted exactly the same, can you find the average by adding them up and dividing by 3? But these weights are all different, so you can't treat them as having the same weights, so you can't just add these up and divide by 3. So to find the average, you'll have to use the weighted mean that we talked about. And the weighted mean is simply a formula, and the formula relies on plugging in the right x's and the right f's. So the question now is which column should be the x and which column should be the f?
Credits is F, grade is X.
Okay, very good. So let's talk about why. So the reason is you're trying to find the mean grade. So the thing that you're trying to find the mean or the average for, that's your x. If you're trying to find the mean number of credits, that wouldn't even make sense in this example, but if you were trying to do that, then the credits would be your x. But in this case, you're trying to find the mean grade, so your grade would be the x variable. And the other thing would be the weight. So in this case, the credits is the weight, or f. So because frequency and weight have the same meaning, you also see this formula in your book as, instead of f, you might see w. So in this formula, instead of the sum of all x times f, you might see the sum of all x times w. But same meaning. Okay, so basically, the weighted mean formula just tells us to find this mean grade. We just add up all the x times the frequency and then divide by the sum of the frequencies. So in this case, basically we're just going to multiply the products of the rows and add them all up. So in this case, it will be 5 times 4 plus 1 times 0 plus 3 times 2. And then we're going to divide by the sum of the frequencies, which in this case is the sum of the credits. So 5 plus 1 plus 3. So go ahead and punch that in and let us know what you get. So just like what we expect, because all these weights are these grades are weighted differently. This A that you got is worth a lot more than the other grades that you got. The average isn't just going to be add up these numbers and divide by 3, which would be a 2.0. This average ends up being a lot higher because this A that you got is shifting that balance towards that A that you got that's worth a lot. So this mean ends up being 2.8. Any questions? So if I gave you a distribution like this, you should be comfortable calculating the mean. And either you can use the mean formula, the weighted mean formula that we talked about, or you should be comfortable using your formula in the statistics mode, where you can just basically enter in these two columns, and the calculator will give you what the mean is, by basically internally using this formula to calculate that mean. And so, again, try to either Google the keystrokes to find the weighted mean, or see me after class, and I'll show you for your calculator. So ultimately, you should be in a position where you just enter in these two columns and your calculator will give you the mean. So one other related idea I wanted to mention was oftentimes, like you saw before with the grade distribution, instead of actual specific values here, you might have a range of values representing each group. So maybe instead of 2, here you might say, so all x values that are between 2 and 5, there's 4 of those that occur in your data set, are between 6 and 8, you might have 6 of those, and 9 and 12, you might have 8 of those. So let's say you were asked to find the mean. So before, if you had a single value for x here, we talked about how to find the mean. That would be simple. So all you would have to do to convert this situation into the previous situation is just find the representative value for each group. So basically we just find the average of this range. So add the lowest and the highest value and divide by 2. So in that case it would be 2 plus 5 divided by 2, which would be 3.5. And you do the same thing for each of these values. So 6 plus 8 is 14, divided by 2 is 7. And then 9 plus 12 is 21, divided by 2 is 10.5. And then now we're back to a situation where we've seen before, and to find the mean, you would simply use this weighted mean formula or use your calculator.
That's way easier than what the book said.
Oh, really? Oh, okay. Do you remember what the book said?
Yeah, it says do your maximum, subtract your minimum, and then divide it by the frequency.
Oh, jeez, okay.
And I can show it to you on the page.
Yeah, that's fine, I was just curious, not that curious. Okay, we have a little bit of time, so. Yeah, since we're talking about the mean, let's continue this. So we've been talking about the mean as one way that we describe the center of a data set, or the most typical value. How else do you think people go about describing the center of the most typical value?
The median?
Yeah, the median, good. So the center is described either with the mean or the median. So do you guys recall how the median is calculated?
The sum of all the data points divided by 2.
Not quite, that would be the kind of the midpoint, but the median would actually be, if you were to take all the numbers and find the middle, the number that's actually in the middle position. And the way that you find that is by sorting all the numbers from lowest to highest or highest to lowest, it doesn't matter, and then find the number that's in the middle position. So basically so data point in middle position. So for example, if you had 87, 95, 76, you would first sort the numbers from lowest to highest or highest to lowest. So let's say we arbitrarily choose lowest to highest, and then you pick the middle number. So the number in the middle position is the 87.
What happens if you have an even number of numbers?
Okay, good, let's talk about that. So in this case, we happen to have an odd number of numbers, but let's say we had an even number of numbers. So we would start with the same thing, which is order the numbers. Let's say ascending order. And then now you notice that the middle position is actually here, which is between two numbers. And so what you would do then is that position that the two numbers straddle, you would take the average of those two numbers, and that would be the median. So the average of 78 and 87. Look, let's see. 82 and a half. So if you have an odd number of numbers, the middle number will be a data point that exists already in your data set. If you have an even number of numbers, the middle number will be between two numbers. So you look at those two numbers, take the average, and that'll be your median. Okay, so let's just continue what we left off last time, or next time.